Okay, calculus. 13.2 is about limits for multivariable functions. Mathematically, they behave very similarly. The only difference is limits in 2 dimensions. You're approaching from either the left or the right. But once x and y are both involved, you can approach from the left, the right, above, below, along a diagonal. You can approach in so many different directions that it's actually a little trickier. And so the first page is about explaining why that is the case. But for our practical purposes, we're going to talk about what it means for us. It's almost the same as 2 dimensions. You're approaching, and as you get closer, your value gets closer and closer to whatever the number is. And of course, the easiest limits for you to take in Cal 1 are ones that you could plug in. And just like here, if the opportunity arises where you can plug it in, you should do so. But let's talk about visually what's happening for a limit. It's as you get closer and closer, coming from any direction to a certain point, what is the value, your z value approaching, or your function value approaching? So unfortunately, the hardest part about this is if a limit doesn't exist versus a limit is a number when you have to check different directions. But let's start off with ones you can just plug in. If the opportunity arises, you just plug the limit in. Let's find the following limits and discuss the continuity. The limit as x, y approaches 3, 1. So this form means your x is going to the first number and your y is going to the second number. So we just plug in 3 squared minus 2 times 1, or 9 minus 2, which is 7. From all directions, it should approach 7. Now, what about the limit as x, y approaches negative 1, 2? Oh, and it says discuss their continuity. X squared minus 2y, this is defined everywhere. It's not like we're dividing or taking the square root, so it should be fine. Limit as x, y approaches negative 1, 2. Should just be able to plug in negative 1 plus 2 over negative 1 minus 2. That's 1 over negative 3 or negative 1/3. Simple as that. Discuss the continuity. It's continuous if it's defined and both the limit and the function are defined. Where is this not defined? When x minus y, the denominator is 0, so x equals y. So we know that it's continuous everywhere that x is not equal to y. Now, if the limit doesn't exist, there's a common scenario in which it doesn't exist along any path, and the less enjoyable scenario where it exists but goes to different values along different paths. And so when I'm talking about path, I'm talking about, let's take the point in the xy plane, let's say here. Normally, before, in 2 dimensions, we could go from the left towards the point, go from the right. Now I can go from above, from below. I can take any diagonal because I have 2 different variables approaching that point. So there's so many ways we can approach it. However, to prove the limit doesn't exist because the limits are different, all you have to do is find 2 limits that are different from each other. And so you'll see some tricks here. Notice that all of those that we were approaching, we're either approaching along a vertical, a horizontal, or a diagonal line. Now, what do we know about the equations of vertical lines? They're x equals a constant. Horizontal lines are y equals a constant. Diagonal lines are some form of y equals mx plus b. So keep that in mind. Determine why the following limits don't exist. Well, the limit as x and y approach 0, 0 of 1 over x squared plus y squared doesn't exist because first off, the function's not defined at that point. But no matter what happens as you get close to that point, it becomes 1 over 0, which is infinite. So the limit approaches infinity, so that's why it doesn't exist. Now, why does the limit not exist in B? Okay, so let's think about this for a second. What happens when we approach along the vertical line? So we approach along the line 0, y. That is, y can be whatever, but x is approaching 0. That becomes the equation negative y squared over y squared, because the x's are 0, which is negative 1 squared, which is 1. So the limit is 1 along the vertical line. What about the horizontal line? It's similar. It's x squared over x squared, which is 1 squared, which is 1. So far, so good. So that covers the vertical and horizontal line, but what about a diagonal line? The best diagonal line is, of course, y equals x. So we have xy approaching, and since y equals x, we're replacing it with x. X squared minus x squared over x squared plus x squared, all squared. Anything minus itself is 0, so this is 0 over 2x squared squared. 0 divided by anything is 0. 0 squared is 0. So this one didn't exist because notice that along the diagonal lines, it approaches a different limit than along the vertical or horizontal lines. If the limit exists at a point, then the function is continuous at that point. For a general definition of continuity, we can say a function of two variables is continuous in an open region, or if f of x is defined and is equal to the limit. So as long as the limit is the same as the function value, then it is continuous. Discontinuities come in two styles. A removable discontinuity is where the limit exists but the function is not defined. Non-removable discontinuities when the function is not continuous and the limit doesn't exist. For example, 5x squared y over x squared plus y squared has a removable discontinuity at 0, 0 because the limit exists. It's because no matter which line, which direction you approach this from, you'll be able to cancel out variables in some way. Now, the one we just talked about has up here, part B, has a non-removable discontinuity because the limit was going to different places, so the limit didn't exist. Okay, continuous functions of two variables. If k is a real number and two functions are continuous, a scalar multiplier of a continuous function is continuous. The product of two continuous functions are continuous. Same as sum and quotient as long as you're not dividing by 0. The following functions are continuous at every point in the plane. Just some examples. We can apply continuity to composition of functions as well. The outer function is the function of one variable. So let's discuss the continuity of these things down below. F of xy equals x minus 2y over x squared plus y squared. This should be continuous everywhere but 0, 0. Because you can't divide by 0, so even if the limit exists, it doesn't matter, it's not continuous. Here, for f of xy equals 2 over y minus x squared, it's continuous except where y equals x squared. So that parabola. So again, it would make you divide by 0. One last thing to talk about. The definitions of limit and continuity can be extended even another dimension, but the same rules apply. So discuss the continuity of f of x, y, z equals 1 over x squared plus y squared minus c. So that would be, we know x squared plus y squared minus z cannot equal 0. That means x squared plus y squared cannot equal z, which means this is continuous except on circles of radius z. And that is all for 12.2.